Greetings and salutations, magical chemists. Let's talk about the glories of gas stoichiometry. There are technically two different ways to do gas stoichiometry, when you're at STP and when you're not at STP. So first, let's talk about what to do when you are at standard temperature and pressure. Well, that means you can use the convenient conversion factor of 1 mole of a gas takes up 22.4 liters of space. And that's true for any gas, well, any ideal gas. And then you just follow normal stoich. So let's go ahead and try a problem like this, using the combustion of propane. So we want to know the volume in liters of oxygen gas that would be required for the complete combustion of 0.250 liters of propane, and we even gave you a balanced equation. How nice is that? So we're going to start out with our given, our 0.250 liters of propane. And since this was happening at STP, I'm just going to quickly convert from liters to moles, using my conversion factor of 22.4. Well, now that I have moles of propane, it's easy enough to convert to moles of oxygen using my mole-to-mole ratio. Where does that mole-to-mole ratio come from? Well, the balanced equation, of course. So according to the balanced equation, for every 1 mole of propane that reacts, 5 moles of oxygen gas will react. So it's a 1:5 ratio. Now, if we wanted moles of O2, we'd be done, but they wanted liters. So now I need to convert from moles of O2 to liters, using, of course, my 22.4 liters in 1 mole conversion factor. So we get a grand total of 1.25 liters of O2 that must have reacted. Now, if you, like me, are a lazy human, you might be looking at that going, wait a second, didn't I do more work than I had to? Because I divided by 22.4, but then again, I multiplied by 22.4, which means mathematically, these two steps just canceled each other out. That leads to an awesome gas stoichiometry shortcut. If you have you're doing a liter to liter conversion and you measured everything at STP, you actually don't even need a mole to mole ratio. There's something called a liter to liter ratio. So let's try that shortcut. This next part wants to know, okay, well, what would be the volume of all the gaseous products that are created, assuming the same amount was reacting as was in the first part? So I'm starting with my same given, my 0.250 liters of propane. And now I'm not going to convert to moles because everything's being made at STP. I'm going to do a liter to liter ratio. Now this ratio is a little bit interesting. So I'm starting with liters of propane because that was my given, but I'm not converting to liters of a specific chemical. They want to know about all the gaseous products. So I'm just going to say liters of products. You might be thinking, sure, this sounds great, but where the heck am I supposed to find a liter to liter ratio? Well, you find it the same way that you found a mole to mole ratio, using the balanced equation. So we're still starting with 1 liter of C3H8 in our ratio, just like there was 1 mole. But now, since we're looking at all the products, well, there's 3 moles of gaseous carbon dioxide produced and 4 moles of gaseous water produced. So in total, that's 7 moles of gaseous products produced for every 1 mole of propane. So we have a 1 to 7 liter to liter ratio. And then the math is easy, 7 times 0.25. And we've produced 1.75 liters of products at these conditions. The best part about the liter to liter shortcut is that it works even if you're not at STP, as long as you're doing a liter to liter conversion and the volume of all the gases is measured at the same temperature and pressure. Because mathematically, 22.4 wouldn't be your conversion factor anymore, but you'd still be dividing by the number and multiplying by the number, so it would still cancel out. So this is the best shortcut. Of course, you're probably realizing by the way I introduced it that you can't always use a liter to liter shortcut. So let's talk about what the heck you're supposed to do then. Well, if you're doing gas stoich and you are not at STP, or it's not liter to liter at the same temperature and pressure, well, then you have to use pivnert, the ideal gas law. You can just use pivnert to find the number of moles if you were provided the volume of the gas, or you could use pivnert at the end to find the volume of gas after you've calculated the moles from stoich. So here's a nice cheer to help you remember. When you're not at STP, use PV equals nRT. Go chemistry! Woo! I know, rhyming is just fun. I can't help myself. If you say when you're not at STP, use pivnert, it doesn't have quite the same ring, but it's still the correct idea. All right, let's go ahead and try a practice problem to see how pivnert might be applied in these cases. And this is a fun example problem because we get to use tungsten, which you may not realize is represented by the letter W. So we want to know how many liters of hydrogen gas at 35 degrees Celsius and 0.980 atm are needed if we want to react them completely with 875 grams of tungsten oxide. Okay, well, you're starting with tungsten oxide. You're converting to hydrogen gas, clearly stoic. And we're starting in grams of tungsten oxide, so we're just doing normal stoichiometry. So we're going to take our given, our 875 grams of tungsten oxide, otherwise known as WOO, or WO3, and we need to convert that to moles, and then we can do a mole-to-mole ratio. Tungsten's kind of heavy, so there's 231.85 grams of tungsten oxide in 1 mole of that. Now we're in moles, we can set up our mole-to-mole ratio to convert to hydrogen gas, the thing we're actually looking for. And we find our mole-to-mole ratio from the balanced equation. Well, for every 1 mole of tungsten oxide, it reacts with 3 moles of hydrogen gas. If we wanted moles of hydrogen, we'd be done, but of course we want liters. Now, if we had measured at STP, we'd just have one more fraction, right? For every 1 mole of H2, it would be 22.4 liters. But hopefully you realized we're close to STP, but we are not at standard temperature or standard pressure. So we need to stop and just solve for the number of moles of H2. And then we can use pivnert to go ahead and convert from moles to liters. Okay, so we have about 11.3 moles of H2. Now I've rounded that for 3 sig figs, but remember on our next step, we're still going to plug in the full calculator answer. So on our next step, we're trying to find volume of H2. So we're just rearranging pivnert to solve for V. And we can just solve by plugging in. We're using the number of moles we just calculated. And of course, we find our R value and, all that good stuff. So as we know, we have 11.3 moles of H2. And then the pressure they gave us is an atmosphere. So we need to use the tiny r, 0.08206. Then, of course, we're multiplying times temperature, and we have 35 degrees Celsius, but, of course, we're going to convert to Kelvin. So that would be 308 Kelvin. Last but not least, divide by the given pressure. And yay for calculators, you get to plug this in, keeping the 3 sig figs. And remember, I'm plugging in the full number that I got on this first step, even though I wrote the rounded answer, because I'm a lazy human. And so, with the glories of math, you would calculate 292 liters of H2 must have reacted with the 875 grams of tungsten oxide. Ta-da! You're done. Hopefully both of these calculation types are familiar. These are things that you learned how to do in pre-AP chemistry, although, reviews are great. You might be thinking, okay, but how can we ramp this up? How can we make it even more fun because we're in AP? Well, let's take a look at one more example problem together. So now we have 34 grams of propane reacting with 18 grams of oxygen gas. And it's in a 0.75 liter sealed bomb calorimeter. No, that's not a bomb. It's just a calorimeter that's sealed. And we want to know, okay, that's awesome. What is the pressure inside after the reaction is complete, assuming that it happens at 25 degrees Celsius? Okay, flashback to good old stoichiometry here. You've been given 2 different amounts, one for each reactant. This is a limiting excess problem. The problem with a limiting excess problem when you're doing gas stoich and they want to know the pressure inside is it's not enough to figure out what's limiting. You do have to do that. That's the only way to do the problem. But you also have to figure out what's in excess and what's left over, because all of the leftover gases and the gases that are produced are going to contribute together to the pressure inside that container. So this was made for a rice table, or Bca table, I guess, since we're doing it in moles. Okay, before we can do anything else, we have to figure out what's limiting. You may or may not remember the quick trick, where you convert each of your given amount of reactants into moles, and then divide that by the coefficient. Whichever number is smaller, That's your limiting. So let's try it. Let's convert our givens into moles since they're both in grams. Well, converting to moles is quick divide by molar mass. So I have 0.77 moles of my propane and 0.56 moles of O2. Don't forget, you can't just compare these numbers. You need to compare the numbers after that we divided by the stoichiometric coefficient. Turns out it is still definitely going to be oxygen gas that's limiting. Okay, now that we know what our limiting reactant is, we can go ahead and set up our rice table, or probably should call it a Bca table because we're working with moles. This is what we did when we were doing titrations and we were trying to see how much stuff was left over at the end. Bca just stands for before, change, and after, as opposed to initial, change, and equilibrium like we have for our rice table. Initially, we have our given numbers of moles for each of our reactants that we just calculated, and we don't have any products. For the change column, you're just showing how much was either gained or lost. Well, the limiting O2, clearly all of it gets used up, right? This goes to completion. It says the reaction is complete. Then we have to do some math to figure out, okay, well, how much of the excess got used up and how much of each of our products are produced. Well, that's just normal mole to mole stoic. Knowing that there's a 5-to-1 ratio between O2 and your propane, well, I must have only used up 0.56 divided by 5, which is about 0.11 if you're rounding for sig figs. So that's how much of the propane actually got used. Then we get to do the same stoichiometry, but we need to do it to figure out how much CO2 is going to be produced and how much water is going to be produced. So, quick and easy. It's a 5-to-3 mole ratio to figure out how much carbon dioxide will be produced, and a 5-to-4 mole ratio to find out how many moles of water will be produced. Now, of course, once you know what the change row is, it's easy enough to figure out what the final amount left afterwards is. You just add the amounts together. So at the end of this reaction, not only have you produced 0.34 moles of carbon dioxide and 0.45 moles of H2O, that's a gas, steam, you've still got gaseous propane floating around in there that didn't react. So when we want to solve for the total pressure in the container, we need to add up the total number of moles inside that container. Since I've got 1.45 moles of gas in total, that's what I'm going to plug into PivNert when I'm solving for my total pressure. So this really is just another doing stoichiometry when you're not at STP problem. It's just also a limiting excess problem. And when you finally solve, you would figure out that the total pressure inside that container is 47 atm. That's a pretty high pressure. All right, well, that is about as fun and exciting as gas stoichiometry can be. So thank you for playing with all of the glories of chemistry.